Good evening. I'm Mark McKinnon with the National Radio Astronomy Observatory. I'm the Assistant Director for NRAO's New Mexico operations in Socorro, New Mexico, where we operate and maintain the Very Large Array and the Very Long Baseline Array radio telescopes. On behalf of associated universities and the NRAO, I would like to welcome you to the 55th Annual Jansky Lecture. The Jansky Lecture Series was established by the trustees of associated universities and the NRAO to recognize outstanding contributions to the advancement of radio astronomy. It is named for Carl Jansky, who in 1932 was the first person to detect cosmic radio waves. In doing so, he founded radio astronomy and opened a new window onto our universe. The Jansky Very Large Array on the plains of San Agustin is named in his honor. We are very fortunate to have members of the Carl Jansky family attending the lecture this evening. They are Gregory Jansky, Carl's grandson. I will ask Gregory to speak on behalf of the family shortly. Gregory is joined by his wife, Dulce, and I believe his brother Chris may also be online as well. Mary Ann Edwards, who was Carl's niece, is also in attendance, as is Matthew Jansky, grandson of Carl's older brother. Also, Charlotte Jansky, Carl's great-granddaughter, is with us too. Gregory, I would be grateful if you could say a few words or introduce anyone in your family in attendance who I might have overlooked. Gregory, over to you.
Good evening. Representing the Jansky family, I would like to congratulate Dr. Haynes on being awarded the 2020 Carl G. Jansky Lectureship. 40 years ago, my dad's cousin Curtis happened to walk into the Charlottesville NRAO building and learned about the yearly Jansky Lecture. Since that time, either my dad, Curtis, or both have attended a lecture in Charlottesville, and I know my aunt has attended lectures in New Mexico. In recent years, more of the family have attended, and we have enjoyed the hospitality, dinners, lectures, and speakers, and for that we thank NRAO for thinking of us. Due to current circumstances, we regret that we are unable to attend in person, but look forward to this year's lecture.
Thank you, Gregory. I appreciate that very much. And again, I welcome your family here this evening. Before I introduce our speaker, a few logistical comments. If you have questions for our speaker this evening, please use the Q&A window at the bottom of your screen. Those will be recorded, and we will answer those at the end of the lecture. Please don't use the chat button to record your questions. Use the Q&A button. Of course, you're free to use the chat button to communicate with one another. We already have a couple of very good comments so far. So let's get on with this. It's my pleasure to introduce this year's Jansky lecturer. Is Professor Martha Haynes from Cornell University, who will be speaking on 70 years of studying hydrogen with radio telescopes, from dark matter to the dark ages. Professor Haynes earned a BA in physics and astronomy from Wellesley College and an MA and PhD in astronomy from Indiana University. After receiving her PhD, she held research positions at the National Astronomy and Ionosphere Center. She then joined NRAO as the Assistant Director for Green Bank Operations. After 3 glorious years in Green Bank, she joined the faculty at Cornell, where she is now the Goldwin Smith Professor of Astronomy. Additionally, she currently chairs the Board of Directors for the Cornell-led Cerro Chajnantor Atacama Telescope, or CCAT. That's a state-of-the-art, high-altitude submillimeter radio telescope in northern Chile. Professor Haynes' research interests include the large-scale distribution of galaxies in the local universe and how the local environment influences galaxy formation and evolution. She co-led the ALFALFA survey, that's an acronym, with the multi-beam receiver on the 305-meter Arecibo telescope. The survey is a census of gas-bearing galaxies in a cosmologically significant volume. The survey data enable the exploration of key issues in near-field cosmology and galaxy evolution. Professor Haynes awards and honors include the Catherine Wolfe Bruce Gold Medal awarded by the Astronomical Society of the Pacific for a lifetime of outstanding achievement and contributions to astrophysics. The Henry Draper Medal from the National Academy of Sciences, presented for a recent original investigation in astronomical physics of importance and benefit to science. A member of the American Academy of Arts and Sciences and the National Academy of Sciences, a fellow of the American Association for the Advancement of Science, and a distinguished lecturer at the Princeton and Harvard Smithsonian Center for Astrophysics. We are delighted to have a scientist of Professor Haynes' stature for the 55th Jansky Lecture. Please join me in welcoming her virtually to New Mexico. Martha.
Well, thank you very much, Mark. It's really a pleasure to be here in virtual space. I admit that I would rather be dining and enjoying the wonderful weather in New Mexico, but here we are. So I think with that, I'll start out. If I can share the screen. So I've chosen this topic for tonight because I think it's useful oftentimes to reflect on the history of hydrogen with radio telescopes. I will also confess to you that 70 years has some importance for some of the rest of us too. So let me start. I don't seem to be able to advance my slides. So I'm going to go back. I should have tried that. Okay, so first of all, over the 70 years since its first detection in 1951, the 21 centimeter line has been used by a very large number of astronomers, some of whom I know are listening to this Zoom call and therefore have me very nervous this evening to make lots of clever and exciting discoveries. In a short talk, I can't possibly mention all the discoveries and I can't mention all the people. And so I want to first of all make an apology to all the people I won't be able to mention and all of the discoveries that I'm not able to call out. And I'm also going to be making the work sound much, much easier than it actually has been. And I hope those of you who are listening won't really think that it's all straightforward and we understand everything, it goes easily. Science is often frustrating and complicated. I also want to apologize for the fact that I'm giving this talk a bit of a personal bias. One of the reasons for that is that you have silly pictures like this where you can show people doing silly things when they're at observatories. So first off, to start off with, I think I have to explain what the hydrogen 21 centimeter spectral line is. Hydrogen is the simplest of all the atoms. It consists of a proton and an electron. In the lowest energy state, that's all there is, and the electron orbits around the proton. At the same time, the two particles spin on an axis, and there are two possible energy states: a slightly higher energy state where they're spinning in the same direction, a slightly lower energy state when they're spinning in opposite directions. And if for some reason they switch from the higher to the lower energy state, then they give off a photon of light, which has a wavelength of 21 centimeters, which is about that big. Hydrogen, the hydrogen that we will be talking about tonight is hydrogen that is at relatively cool temperatures. We also have to realize that hydrogen comes in other forms. It can be cold, in which case it's molecular. It can be hot, in which case it's ionized. But we're going to be focusing on the cooler temperatures of a few hundred to a few thousand degrees is what I mean by cool. And in the case of this 21 centimeter photon, it has a wavelength of exactly 21.106 centimeters when the source is at rest. And that corresponds to, in radio astronomy speak, where we like to talk about frequencies, 1.42 gigahertz or 1420 megahertz. The signal that we get from a galaxy that tells us about the hydrogen in the galaxy looks something like this little cartoon here. It has a characteristic two-horn shape. It's centered at some frequency, and then over a range of frequencies, it gives off some intensity of emission. And so that's the signal we're looking for. It's very characteristic. It allows us to understand something about the galaxy. In particular, there are three pieces of information that we really get, which I'll come back to and refer to later. First of all, the frequency can be shifted from this rest frequency, which is given up above. And the amount of that shift tells us how fast the galaxy is moving away from us, or in a few cases towards us, but in most galaxies moving away from us. So we get what we call the Doppler shift. Then the area under the signal, as I've sketched out here in this gray, the area tells us essentially how many hydrogen atoms there are. And since we know how much a hydrogen atom weighs, we can add up all those hydrogen atoms and we figure out the mass of the cool hydrogen in the galaxy. And then the third piece of information we get is what we call the width of the line. And since frequency and velocity are related, the spread in the line tells us something about how fast the gas clouds of hydrogen in the galaxy are orbiting around in the dark matter halo, as we'll talk about later, of the galaxy itself. So the spread of the line tells us about the rotational velocity. The shift of the line tells us about the recessional velocity. And all of that provides us with a lot of information about the galaxy from which this signal originated. So let me go back and explain what a galaxy is in case that's not a familiar thing. So I come from Cornell, you all know that. Therefore, a galaxy contains billions and billions of stars. And this is a galaxy which I've chosen specifically because we think that if we could step outside our Milky Way galaxy, our galaxy, the Milky Way, would look something like this. And so I want you to think about what you see in this image. First of all, the bright points that you see when you look at an optical image are due to stars in the Milky Way. We have to look out of the Milky Way to see a galaxy in the distance. The optical light that you see that makes up this picture comes principally from starlight. It doesn't come from the cool gas, it comes from starlight. Notice also that the galaxy has structure to it. This galaxy Messier 81, as we call it. It has kind of a bulgy region in the center, which looks more or less solid, but then it has these spiral arms coming out from the bulge region. They're located in a disk, and that disk is tilted with respect to our viewing angle, and therefore it looks kind of elongated or oval. If this were in fact the Milky Way galaxy, then the sun and the solar system would lie about 2/3 of the way out in the disk. In fact, the solar system is located about 26,000 light years away from the center of the Milky Way galaxy. And let me just remind you that light year is the distance that light can travel in a year. So we like to talk in light years because in astronomy, what that means is that if we observe the galactic center from our location, we're observing light that left the center 26,000 years ago. That's going to be very important to us because it allows astronomers, in fact, to study when we study the universe, we look out into space, we're looking back into time. But a galaxy doesn't just contain billions and billions of stars. It also contains gas and dust clouds in between the stars, what we call the interstellar medium. And the gas that we are studying with the 21 centimeter line comes from the interstellar medium of a galaxy. In this case, notice that we see some evidence of the interstellar medium of this galaxy. I said most of the light that you see here comes from stars. The pinkish patches come from hot ionized gas at about 10,000 degrees Kelvin. And the brownish darker patches, which you can see here and here along these spiral arms, come from cold molecular gas and dust clouds, which are at about 30 degrees. The hydrogen that we're going to be talking about tonight is the cool gas at a few hundred to a few thousand degrees, which is not visible in this image. Just to put that a little more in context, here are some close-up images of gas and dust clouds in our Milky Way so that you can see what I'm talking about. Here's a wide-angle view of the Milky Way galaxy, which you could see if you were out someplace in a nice clear view like in New Mexico. Not so easy to see in a place like Ithaca, New York, where I am, but in beautiful places like New Mexico, you get this fabulous view. And my real point here is to just remind us that when we look at an optical image from the Hubble Space Telescope, for example, most of what we see is the starlight. But there's a lot of interstellar gas and dust. Here you see the dark patches are the dust, cold dust, which is blocking the view of the stars from behind it. The 21 centimeter line sees the cool gas that doesn't show up in any of these optical pictures. But that leads me to just remind you that of what radio astronomers do not do. We do not sit out in the middle of the desert with our laptops listening with our headphones, nor when we report important discoveries do we say in the middle of the night, I heard a strange beep beep. Instead, we record our signals digitally, we correlate them, and then we analyze them using computers. This other stuff might be catchier. The work that we do is actually hard work and is not so immediately satisfying all the time. In terms of the cool atomic hydrogen in the Milky Way, let's just say that here's a picture of the entire Milky Way galaxy looking over the entire sky. Remember, we're inside it, so it's looking up and above and all around. In this case, the important point is it shows that the cool hydrogen gas here, the highest intensity of that is located in this thin disk that I was talking about, that most spiral galaxies have. It's estimated that about 4% of all of the matter that we can see in gas and stars in the Milky Way, the luminous matter, is made up of this cool hydrogen gas. That it's only 4%, but that turns out to actually be 5 billion times the mass of the sun. So it's not a small amount. Now, it's also true that stars form out of cold molecular gas clouds, not directly from the cool atomic gas, but those cold molecular clouds form when the cool atomic clouds condense and collapse. And so you can think of is the atomic hydrogen isn't directly related to star formation, but it's the fuel reservoir for future star formation. And that's why it's important to try to understand how the fuel reservoir starts out as atomic hydrogen, then goes to molecular hydrogen and eventually forms stars. So atomic hydrogen isn't the whole answer to everything, but it provides a very critical clue that allows us to understand how a galaxy might be able to form stars in the future, and a galaxy that doesn't seem to have any atomic gas probably doesn't have a very good future for star formation either. So to summarize a little bit of what we're going to be talking about tonight, I want to point out again that there are 3 pieces of information that we get from one of these 21 centimeter line signals that tell us fundamental things about the universe and galaxy evolution. The redshifts, the shift of the frequency or the wavelength from the rest frequency, tells us something about the distance to the galaxy. Hubble's law tells us that the further away a galaxy is, the faster it's moving away from us. So if we can measure the shift from the rest frequency of 1420.4058 megahertz, we can figure out how far away the galaxy is. At least the first order. We'll come back and talk a little bit about how that doesn't always work later on. That tells us where all the gas-rich galaxies are. The second thing is we'd like to know how much hydrogen a galaxy has and where the gas in that galaxy is. So here's a picture of another spiral galaxy, the Andromeda galaxy. This is a picture of that galaxy taken in the 21 centimeter line. And you can see that in the center, there isn't much gas. And then in the disk, again, this disk is inclined. There's a lot of gas and it goes far out from the center. When we make a measurement of the 21 centimeter signal, we get the hydrogen mass, as I mentioned, and in some cases, we are able to figure out where the hydrogen is. In other cases, as we'll learn, we just get the hydrogen mass. But in all cases, we can learn about the potential for future star formation. We can learn about whether galaxies in certain regions of the sky have more hydrogen or less hydrogen. And we'll find out that galaxies in clusters are deficient in their hydrogen. They have less hydrogen than galaxies that are out in the middle of nowhere. And we'll also see later on that we can learn about how galaxies actually interact with one another. They exert gravitational forces on each other and can distort and change the evolution of a galaxy. So these properties, the hydrogen mass and distribution, tell us about the evolution of the star formation fuel reservoir. Then the third thing we can measure is the width of the line, the spread of the line, and we'll learn that that tells us about how the gas clouds are moving within the galaxy itself. That gives us evidence for the presence of dark matter in galaxies. And we'll also see that we can use a relationship that has been studied by Brent Tully and Rick Fisher using NRAO telescopes, where we figured out that you could make another measurement of distances to galaxies that's independent of the redshift, which allows us to test Hubble's law. And in the end, we're able to learn from the rotational velocities then where the dark matter is and how much there is. So this is the rest of my talk, or the middle part of my talk, is going to be trying to show you how we've done this over the last 70 years and made really fundamental discoveries, giving us insight into cosmology and galaxy evolution. So back also to our picture of the galaxy, in addition to the billions and billions of stars and the gas and dust clouds in the interstellar medium, galaxies contain a lot of dark matter. And if I could take a picture of a galaxy in dark matter, of course, it would look like that. Because dark matter is dark because it doesn't give off electromagnetic radiation. So we can't see it. So I can't show you a picture. But the key, as we'll be talking about a little bit, is the 21 centimeter line can tell us that the dark matter is there, even if we can't actually see it. So back to a little bit of history. The 21 centimeter line was predicted to be at a wavelength of 21 centimeter when Hendrik van der Holst in 1944, who was given the problem of thinking about the structure of hydrogen atoms and what spectral lines they might give off, he came up with the idea that there should be this strong line of the ground state, of this spin flip, as we say, at 21 centimeters. Then the signal was actually detected by Harold Ewan and Edwin Purcell using the horn antenna, which now resides in Green Bank, which many of us know with great familiarity. The line was first detected on March 25th, 1951. And as I mentioned before, I wasn't alive then, but it was close. So first, we're going to talk about observations done with single dish telescopes. And here are some of our favorite telescopes: the 140-foot telescope in Green Bank, the Green Bank telescope, the Arecibo 305-meter telescope, and the late 300-foot telescope in Green Bank. And I will just say that I started out doing my PhD research just a little bit before the first Jansky lecture. I used all of these telescopes, and it's been quite an exciting ride doing so. We have measured distances, gas masses, and rotational velocities, and putting all this information together from many people over many years, there are some very important conclusions that astronomers have come to. First of all, curiously, high mass galaxies contain less mass in gas than in stars, but many low mass galaxies actually have more of their mass in gas than in stars, which means that it's actually easier for radio astronomers sometimes to study them. And a second important conclusion about galaxy evolution that the 21 centimeter line studies have contributed to in a great way is that the hydrogen content, the gas content of galaxies, depends on the local environment of the galaxy, where the galaxy is. So let's think about some of that. And again, my personal stories. Going back to when I was a graduate student with Mort Roberts, as a graduate student in residence in Charlottesville, and then immediately thereafter as a postdoc in Arecibo, we went out to exploit, and by we, I should say principally myself and my husband, Riccardo Giovanelli, we went out to use the 21 centimeter line to try to study where the gas-rich galaxies are. And we did that principally by measuring redshifts. It turns out in Arecibo in those days, there were lots of people who were interested in studying one part of the sky, and nobody else cared about the other part of the sky. And we were on the staff there. So we decided to look at the other part of the sky when there was not much pressure on the telescope. We did notice that in about 1932, Walter Bernheimer pointed out that there's a region on the sky, and here's a sky plot, right ascension and declination for those black belt astronomers here, just showing the distribution of galaxies in a part of the sky. You can see there, the darkness here means more galaxies. So this is what's called the ridge of the Pisces-Perseus supercluster. It was known to us in Arecibo, of course, as the extragalactic lizard, because we were in Arecibo. What we realized when we measured a few thousand galaxies, one at a time, by the way, taking a lot of telescope time over a long period of time, was that if we look, remember we said before that Hubble's law tells us that the velocity of the galaxy away from us tells us about the distance. These galaxies that lie along this ridge also have largely the same velocity, which means they are all at the same distance from us. And this struck us, another friend, Peppo Gavazzi, who's a wonderful artist, made a little picture of what this supercluster looked like. And while at the time there wasn't a real clear picture of the large-scale distribution of galaxies in the universe, it struck us that this was a filament. Well, Riccardo thought the universe was a bowl of spaghetti, but I thought it was a filament. And nowadays, when people make visualizations of the distribution of galaxies on very large scales, hundreds of millions of light years, they point out this, what we call the cosmic web. And again, I think it's fair to say that we were lucky to be the right people in the right place, making these observations at a time when radio astronomers were really able to make detections of lots of galaxies over a very large scale. And therefore, we discovered the filamentary structure of the universe. Mark mentioned that in more recent years, Ricardo and I have been the PIs of what's called the Arecibo Legacy Fast ALFA survey, where ALFA is, here's my 7-pixel hornbeam camera known as the Arecibo L-band feed array, or ALFA. So in fact, Mark, ALFALFA is an acronym with an acronym in it. But ALFALFA sounds cool, so that's okay. And I wanted to show you the kind of signal that we would find on occasion, or rarely, a signal from, I think it's fair to say, my favorite galaxy. Here's the 21 centimeter line signal. So here's just static radio noise. Here's a signal from the Milky Way galaxy, which of course is right next to us, so it's very strong. But we see a strong signal that you can see here from a source given this delightful street address, also known to us as Leo P. And here's a VLA map. And you can see it's a clear source, but it really stood out in a survey like the ALFALFA survey. And what's curious about this is if we take a look at this Hubble Space Telescope image, you don't see a very prominent looking galaxy, do you? Now, in order to take a look at this a little bit closer, I'm going to get rid of that star in the foreground, which is kind of distracting. But let me just point out that this galaxy, which we call Leo P in the constellation of Leo, P because it's pristine or primordial, although many of the people, or some of the people out in the audience tonight know that it's actually Leo, P stands for prosciutto, because of its discoverer. This image was an HST image taken by Christy McQuinn. If you just look at a standard image, not at something where you've proposed and the Hubble Space Telescope folks have given you time to look at it, it's barely visible, and yet you saw the signal before, it's clearly evident in the radio survey. And so that's really my point, that this galaxy is in fact so nearby that Hubble sees the individual stars in the galaxy. And what's really relevant to this talk is that this galaxy has more of its mass in gas than it does in stars. And so it stands out to radio astronomers. In fact, optical astronomers had categorized it as a distant cluster of galaxies, not a very, very nearby galaxy. So radio astronomers are able to discover galaxies that might be missed by optical astronomers. Now, next thing that I've mentioned a little bit before, but I want to bring up again, is the spread of the spectral line that we've talked about. So here's our cartoon diagram of what we get. Here's what I mean by the line width. And in order to understand that, you have to think about what is happening. We have gas clouds in the disk of a galaxy, and they are orbiting around the center of the galaxy. So here's my little cartoon. They orbit around at a constant distance from the center of the galaxy. They sometimes have a little bobbing motion up and down, but their main motion is rotational motion. And then what was noticed in 1977 by Brent Tully and Rick Fisher was that the brighter and more massive galaxies rotate much faster than the small, less mass, fainter ones. And so they came up with something called the Tully-Fisher relation, which relates the rotational speed to the brightness or the luminosity or the mass of the galaxy. That is called the Tully-Fisher relation. Over the intervening period of time, other astronomers have refined it a little bit. In particular, Stacy McGaugh and his collaborators have shown that if you replace the stellar luminosity with the mass in gas and stars, you include the mass in the gas also, you get an even better relation that you can track over a much wider range of mass. So we have these relation, you can measure the width and you can measure the mass in stars and gas, and you can use this relation, as Brent and Rick noticed, This gives you another way of measuring the distance to a galaxy, because you know its luminosity, you observe its apparent brightness, you get the velocity width, you have this relation, you can calculate the distance, and this distance does not depend on the observed redshift. So you can test Hubble's law. Does Hubble's law really work? And it turns out that Hubble's law works well, but not perfectly. And that's because the universe isn't all smooth. And while the expansion of the universe should be a smooth expansion, where you have lumps and bumps of material, where there are massive clusters, around those clusters, the expansion of the universe is slowed down locally. And in other regions where you have no galaxies, the expansion is not slowed down, and you get flows of galaxies, what we call departures from smooth Hubble expansion, or we call them peculiar velocities. We measure these peculiar velocities by comparing the distances given by the redshift and those derived from the Tully-Fisher relation. And that allows us to recreate where the dark matter in the universe is. So here we have a cartoon picture of the local universe. Just to put us in perspective, we're in the center. Here's the Pisces-Perseus supercluster. This is on a much grander scale of hundreds of megaparsecs. But you can see that the galaxies aren't randomly distributed. They follow along this filamentary structure, this interwoven filamentary structure. And around the regions which have more galaxies, the overdensities, you actually find that the expansion of the universe is slowed down. So this little diagram from Tully et al. Shows their recreation of the distribution of galaxies and matter in the universe that is based on tracing the motions of the galaxies using the Tully-Fisher relation. And so they discovered that what we used to call the local supercluster is part of something grander than that, called the Laniakea supercluster. Here's the Pisces-Perseus supercluster kind of in the other direction. We are here. And there are also regions, the blue ones, where there is no dark matter, there is no luminous matter. The universe is really underdense. We call those voids, and they're almost as important as the superclusters. So the conclusion, a very important conclusion from cosmology derived from some of these observations of the Tully-Fisher relation, there are many of them, I've only mentioned a few, is that light traces mass, including the dark matter, even on huge scales of hundreds of megaparsecs. So dark matter is important within galaxies. It's also important on very large scales. So now let's move on to taking into account the information that you get from interferometers. What interferometers like the VLA can do is they tell us where the cool hydrogen gas is. It's found in disks. The disks are often bigger than the stellar disks. In spirals, you often see a hole where the bulge is. You see the spiral arms though, and curiously, there are only one or two what we would call elliptical galaxies here, because elliptical galaxies, ones that don't show the disks and the spiral structure, have almost no cool gas. Interferometers also tell us where the gas is not. And in this beautiful image made by the Virgo Viva survey, again with the VLA, you see an image that includes the X-ray emission from hot intercluster gas, and then images of galaxies that have been detected and mapped with the VLA around the center of this cluster. And notice that the ones on the outside are really quite beautiful and nice, but the ones on the inside all seem to be very, very tiny. And the reason for that is that this hot gas is sitting there, and the cool gas moves through it and feels the wind of the hot gas. And the gas is swept out, and therefore, and then is heated up also, and therefore the cool gas is gone. And so we find out that the galaxies in clusters towards the center are deficient relative to their counterparts on the outside, and they're also smaller because what we call the ram pressure stripping of the hot intercluster gas that shows up in X-rays eats the gas disks and the galaxies from the outside in as the galaxies move through the hot gas. Now let's take a look again at the spiral galaxy Messier 81, because I want to show you again the power of interferometers to be able to tell us the life story of a galaxy, even beyond what you might see. So here's M81. I tried to show you it before as a canonical, simple galaxy like the Milky Way. And remember, the optical image shows us starlight. To be able to show you this in comparison with some other images, I need to rotate the image. So I've just taken it and I've rotated it. And then I zoom out and I get another image. And now you can see that this galaxy isn't alone. It has some friend galaxies close by. In fact, it isn't by itself. It's part of what we call a group of galaxies. A group is a collection of galaxies, a system of galaxies. They orbit around the common center of mass. They all lie at the same distance from us. And just like villages, towns, and cities, galaxies can be found in different environments. We can have clusters, which have this hot X-ray gas, where there are lots and lots of galaxies. We can have groups with only a few. So using the 21 centimeter line, we try to explain something that I tried to explain to my mother, who was a first grade teacher, by saying that what I did was I studied extragalactic sociology, how galaxies are affected by their environment. And so I want to show you an example of how M81 has in fact interacted with its neighbors. And so here's the hydrogen picture published by Yun et al. In 1994 from the VLA. And here's the optical picture. Here's the galaxy M82, and here's the other galaxy at the bottom. But you can see that the hydrogen is clearly interrelated. Something has happened. And I'm going to show you an animation from Mingyun. You know, you can go to YouTube and you can find much fancier, but I like to show you the ones that were used for people to really understand what was going on. We didn't have all the fancy graphics, but we understood the physics. And so what has happened here is this galaxy, the green one, starts at the top. The yellow one is going to show up from the bottom. They come by Messier 81. The tidal pull of the gravity of each of the galaxies stretches out the galaxies, and we end up with the beautiful VLA picture. We are able to recreate the scene and the process of this evolution because of the 21 centimeter line observations, which also tell us not only about the distribution, but also how the particles have moved. And another thing to talk about galaxies is what the 21 centimeter gives is, remember, we go back to this idea that we have clouds orbiting in a disk. They're held in their orbits by gravity. When we look at the optical image of the galaxy, it looks like this. When we look at the radio VLA image of the galaxy, it looks like that. It's much, much bigger. We can study the velocities of the gas clouds in the outer part. We ask, how much mass do you need to keep that hydrogen in their orbits and not from flying out or not from collapsing back down? That convinces us that there has to be, in this region, out in the outer edge of the galaxy, a massive halo of dark matter. The evidence for that is we look at the rotational speed as a function of distance from the center of the galaxy. Here's what the starlight tells us, but the 21 centimeter observations take us much, much further out. If all of the mass were in the stuff that we can see, the hydrogen, the gas, the dust, then we would expect the rotation curve to fall off, but instead it keeps on going up. There must be a dark matter halo. So I'm going to bring the part that we understand to a conclusion by just telling you that over the last 70 years, we have learned a tremendous amount about galaxy evolution, about how galaxies convert their gas into stars, about how local environment governs galaxy evolution, and we've learned about how dark matter is distributed both in galaxies and on large scales. But I'd like to spend the last couple of minutes talking about the incredible future that lies ahead. Remember that looking out to larger and larger distances away from us lets us look back to earlier times in the history of the universe. Let's also remember that more distant galaxies will have their 21 centimeter line redshifted to longer and longer wavelengths or lower and lower frequencies. There are projects now underway and also being developed for the future that's going to allow us to look at how the evolution of gas in galaxies has taken place over cosmic history. Remember, the universe is about 13.7 billion years old. Optical astronomers have found that the period about 10 billion years ago was the epoch that we call cosmic noon. That's the epoch when most stars in the universe were formed. It's the epoch of most intense star formation in the universe. What we'd really like to know is that picture of how molecular clouds form stars, but they were formed out of atomic hydrogen. If we understand how the gas content of galaxies traces the same history as the star formation history. There's a survey that's been ongoing for some years that's producing results now using the VLA. It's called Chile's, led by Jacqueline Van Gorkum. It is looking over about 5 billion years of cosmic history. There are other surveys planned to look out further, including the Laduma survey, which will be done with the Meerkat instrument in South Africa, and future surveys done with the VLA and eventually the NGVLA and the SKA, which will really allow us to put the picture of how stars have formed and how that has evolved over the universe together with the gas content. And the molecular studies will also be contributed by the VLA and ALMA. Again, radio astronomy and optical astronomy, they provide us with different ways of measuring different vital clues to tell out the story of the evolution of galaxies in the universe. Another important thing that 21 centimeter line observations in the future will allow us to do is to take a look at that filamentary structure that I talked about. This is a snapshot of images taken from this rotating little animation. At earlier times in the history of the universe, we think that the structure in the universe was much smoother. And gravity, while the universe has been expanding locally, the concentrations of mass into clusters and superclusters have been dragging material together because gravity is attractive. What we'd like to understand is how that filamentary structure has developed and how the universe has been expanding. At earlier times, the filamentary structure was less pronounced, but our understanding is that the very large structures in the universe have a characteristic scale. They have a characteristic linear size. If we can trace that linear size while still understanding the evolution of galaxies and all the complex things that go on locally, then we can learn something about the geometry of the universe. And so I have just a couple of cartoons here to try to represent that depending on whether or not you have dark energy, this mysterious force that's causing the universe's geometry to accelerate in its expansion, or whether you don't have any dark energy, the geometry of the universe, and therefore how you observe this characteristic linear size will change. And so there are a bunch of experiments that are being designed now. They're called intensity mapping experiments, where we don't measure individual galaxies one at a time, but rather we measure the size of these superclusters or the things that preceded the superclusters. And so in my little cartoon that I have over here, we would look at patches in the distribution of atomic hydrogen over the scale of the universe, and would look to see how big these superclusters, this characteristic size, appears to us. And going back to the previous slide, you can see if you look back, the characteristic size from out here going back or out here going back is not the same. And so if we can measure those sizes and how they change with epoch, which means how they change with us looking back at different frequencies and longer wavelengths, we can learn something about dark energy in the universe. And I'll just say, this is a really tough experiment. Some early results were shown that the method is feasible using the GBT. There are observations going on with a number of facilities around the world. People are trying to make this work using the GBT, the CHIME facility in Canada, and a bunch of others. Watch out, this will be done in the next 10 years of 21 centimeter line research. The last thing I want to mention is even harder. That stuff was really hard. This is really, 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 really hard. But again, the 21 centimeter line gives us classic insight that no one else gets. And that is because if we have a picture of the universe where here we are today and here 13.7 billion years ago, we had an event occurring everywhere in the universe called the Big Bang, there was a period before there were any stars, before there were any planets, before there were any galaxies, when in fact the universe was filled with cool atomic gas. This is what we might call the dark ages. The universe was filled with neutral hydrogen. There weren't any stars. The hydrogen was warmish, but cool, not ionized, not molecular. But because it's looking very far back in time, that 21 centimeter signal is very redshifted to very low frequencies. By tuning to lower and lower frequencies, we actually ought to be able to look through the epoch of reionization, as we say, which is one of the things that the James Webb Space Telescope will be looking for. It will be looking for the first sources of light. We will be looking for the sources of the emission from the gas before those first sources of light formed. So in fact, we ought to see earlier than what the James Webb Space Telescope will be able to see. There's a possible detection of the first signal that was made a couple of years ago by the EDGES experiment, and there are a bunch of other experiments that are underway. There have been experiments done, prototype experiments, trying to figure out how to actually do this that have been done in Greenbank for, I don't know, I think 10 or 15 years. There's an array being built in South Africa, and there's real potential that we will be able to observe and detect neutral hydrogen from before the time before the first stars and galaxies ever formed. So I finish up with a little bit of perspective I hope I've given you, that the 21 centimeter line has provided a very rich scenario for discoveries on where the galaxies are, how gas is converted into stars, the influence of environment on the evolution of galaxies, and the evidence for dark matter in galaxies, mainly in the current universe. What's really exciting for the future, I think, are the studies that allow us to explore the deep, dark past universe using the 21 centimeter line. And so I would have to say, I know it's been an exciting 70 years. I think the next 10, 20, 30 years are going to be even more exciting. And I think that's the best way that someone at my stage in my career can end up, is looking forward and hoping to be able to be part of it in some way. I'd like to just end by saying that I have, through my career, been inspired by a great number of people, some of whom are older than me, but a very large number of them are younger than me. And I just want to say thanks to all of my former students and colleagues, and especially the members of the ALFALFA team, the undergraduate ALFALFA team, to my co-conspirator in all attempts to get as much telescope time as possible, Riccardo Giovanelli, and to all the other people who make science fun for me. So thank you very much.
Thank you very much, Martha. So I'll remind people that that was actually, let me back up. Martha, that was a very educational and entertaining talk. It's also, I think, inspirational to see what has been accomplished in the last 90 years, what we've learned about our universe since Carl Jansky's original discovery. Again, everyone, if you would like to ask questions of Martha, please do so by typing into the Q&A button at the bottom of your screen. If you have some comments you would like to share, that's what the chat window is reserved for. Martha, we have a couple of questions already, and you might want to continue sharing your screen to answer some of these. So I will jump into that. Let's see. One of our first questions, what is the difference between atomic versus molecular hydrogen?
Well, atomic hydrogen is really just when you have a proton and an electron. And molecular hydrogen, you get the two atoms, they get together and they form a molecule. And so there are actually two protons associated. And that form of hydrogen exists at cold temperatures. And then if you give the two protons enough energy, they'll go off on their own. And then you get atomic hydrogen.
Thank you very much. Next question. Are there any other methods to detect dark matter and dark energy apart from the 21 centimeter line?
Yes, certainly. That's a great question. So let's remember that we detect it indirectly. We're not actually getting any signal from like a photon. Dark matter doesn't give off photons. We're indirectly detecting it. We're sensing that it's there. There are ways that one could potentially actually detect the signature of energy given off by dark matter. And there are experiments that are trying to do that. There are other ways that you can sense the presence of dark matter in particular. One is that light is bent around massive objects. And so both radio and optical astronomers sometimes see a phenomenon which is called gravitational lensing, where light from a distant object is bent around a foreground object, the dark matter halo of a foreground object, and you see multiple images of the background object due to the dark matter in the foreground object, the lensing object. And so there are other measures of dark energy, and there are and dark matter. Again, as I tried to say before, in order to explore the universe and all its complications, what we astronomers like to do is have different methods to look at, to explore the same phenomenon. So we can be sure that what we're seeing can be uniquely explained by the presence of dark matter or dark energy.
Thank you, Martha. Another question. How does the rotational velocity give information about the distribution of dark matter if you can't observe its redshift?
What the way we look at the dark matter distribution, I'm going to go back a few slides here to that one, is again, we get this, we're able to observe the motion of the gas clouds in the galaxy at different distances from the center. And as we know in the solar system, all of the mass, the 99% of mass of the solar system is in the sun. The planets are there, but they don't matter much. Jupiter matters a lot. The Earth doesn't matter very much. When we look at the rotational speed of the clouds, their orbital velocities around the center of the galaxy, and we look further and further out, we see that the galaxy ends. We see that the starlight ends. The hydrogen is out here, but the hydrogen is not as massive in this galaxy as the starlight. But the starlight is concentrated in here. When we get out here, we can ask ourselves, well, how fast are these clouds moving? And can we understand how fast they're moving by the mass in the visible disk? And we see that there's a big discrepancy. These gas clouds are moving too fast. Yet the galaxy seems to have existed for a long period of time. So there must be some gravitational force that is holding on to these gas clouds in the outer part of the galaxy. It's not contributed by starlight, and it's not contributed by gas or dust or anything else. It's contributed by something we can't see, and so we call that dark matter.
Thank you, Martha. The next question. What's the oldest 21 centimeter photon that we can currently detect?
What's the oldest? Well, that kind of depends on whether or not you think we've detected whether the EDGES experiment has actually detected the signal from the dark ages. And that if that observation, again, I'm not questioning the result more than the people who presented the result. It's a very difficult experiment. You have to prove and verify that something else isn't going on. That would be a signal from way back in this epoch, looking back to only 100 million years, say, after the Big Bang. The most distant red shifted line that I think we've seen is looking back a few million light years, a few billion light years. We still have a way to go. We're not there yet.
Here's a more personal question, Martha. How did you get into 21 centimeter astronomy of the universe?
Well, that's an interesting question. I was a summer intern at the National Radio Astronomy Observatory in 1974. And I worked with Dick Schrammick, who those of you in New Mexico, I'm sure know. He was my mentor. And I was interested in pursuing radio astronomy. I had been a summer intern the previous summer at Arecibo, but it turns out that my thesis advisor at Indiana didn't get tenure. And so the prospect of my doing radio astronomy at Indiana wasn't seeming very promising. But there are a whole bunch of radio astronomers who did their theses at NRAO who come from Indiana. A few that I can throw off are Yorvant Terzian, Jack Burns, Ricardo Giovanelli, Ed Churchwell, I think. And so there was always this possibility that maybe I could go to NRAO to do my thesis there. And Mort Roberts, I believe, was on sabbatic somewhere that summer, and so I never met him. But Dick Schrammick said, you know, I think you might get along with this guy, Mort Roberts. And I guess he told Mort Roberts, maybe you would find this student interesting. And so we met in the lounge in Greenbank, and Mort interviewed me. And here I am. And I think he's on the Zoom call. So here we are.
Great. Hey, thanks, Martha. I've got sort of a related question. There's some fan mail coming in here. It's an honor to be listening to you today. But in a similar vein, hang on, my question jumped around on me. How did you first become interested in becoming a physicist, and what made you interested in studying astronomy?
Well, I'm the youngest of 5 children. My father was a self-employed manufacturer. My mother was a first grade teacher. My oldest sister, who was also on this call, I believe, this evening, was studied English literature, got her, very proud of her. She got her PhD when she was in her 50s. She's awesome. But the rest of us, for some reason that I don't understand, all studied physics or engineering. And so when I came along, it wasn't that unusual that that's what I would do. I will say that the way I became interested in astronomy was I was 13 years old and I had a lucrative babysitting job, and my elder brother, who had a girlfriend and a car, decided he wanted me to buy him a telescope. So I gave him $30. He sent away for the telescope. I became the astronomer. He did marry the girl.
Another question. Here's another fan who used alfalfa data for part of their REU project this past summer. And the project this person was engaged in was related to the Tinley array, which I hope I pronounced correctly. Are you involved with that project as well?
I'm right at the moment. I try to keep up with the various projects. I'm excited about lots of the projects, but I have more than enough to do. I'm trying to build a telescope in Chile at 18,000 feet.
Not an easy task. Martha, can temperature account for the lack of a radio signal in certain regions of the universe?
Yes, absolutely. If as I said, the 21 centimeter line comes from cool hydrogen of 100 degrees up to a few thousand degrees. If the gas is colder, then the atomic hydrogen becomes molecular and it gives off molecular tracers. If it's too hot, then the electron jumps away from the atom and you get ionized hydrogen, and you see that at optical wavelengths. If it gets even hotter, then you see X radiation. But the spectral line signature from hydrogen 21 centimeter line is pretty much telling us that we have gas that's between 100 or so degrees and a few thousand degrees. So elliptical galaxies do not have much hydrogen and much cool gas.
Let's see, we'll take a few more questions. It's after the hour. Here's one that's very interesting. Are there explanations for how hydrogen gas was formed in the first place?
Well, our understanding is that in the very early universe, there were exotic particles, and then after a while, we ended up forming hydrogen atoms, and after about the first 3 minutes. And so hydrogen is the simplest thing there is. There's a lot of hydrogen in the universe. It's most of the atoms in the universe are hydrogen. Again, our understanding for that, that places strong constraints on what happened in the first 3 minutes of the universe and how the universe was expanding at that time.
Okay, we'll take the last question here. How do we know that dark matter has a halo or spheroidal distribution even in spiral galaxies? And why doesn't gravitational interaction tend to move it into a distribution more closely resembling the parent body?
Well, in fact, even if we look at a spiral galaxy, we see that, now I'm losing my voice. We see that there are stars in a halo that is roughly spherical. And the dark matter halo is even bigger than that. It's just that the stars that we see formed after the gas collapsed into a disk. And that happened because there was a little bit of rotation. And once you get a little bit of rotation in a body that's not perfectly spherical, it will collapse along the axis of gas will collapse along the axis of rotation. And so the stars that formed later formed in the disk, but the halo was already there. And the dark matter halo is bigger than the halo of stars. But so what we only see is part of the entire structure.
Thank you, Martha. You do one more question?
Sure.
Voice will hold up. Except for finding the optical counterpart or not, how do you distinguish the H1 emission from galaxies and the galaxy component? For example, a high velocity cloud in the Milky Way, tidal debris from the profile itself.
Well, the main reason that you do that is by looking at the shift, the velocity shift, because that tells you the distance. Now we can come back and talk about high velocity clouds in a minute, but when in alfalfa, when we reduced the data, not only did we find the signal, we then looked at an optical image, and in 97% of the cases or more, there was an optical galaxy that was associated with a 21 centimeter signal. It was obvious it was a star-forming galaxy. A large number of them did have redshifts measured, and the redshifts were the velocities were coincident. An optical astronomer measured and what we measured were the same. In other cases, there is no optical redshift, but once you observe the first 15,000, the second 15,000 probably behave the same way. Now, there are some cases that are very curious, the high velocity clouds that somebody mentioned. And the high velocity clouds could be in the Milky Way, or they could be very nearby. They're high velocity because their velocities don't fit the usual picture for how gas clouds in the Milky Way are rotating, but they're at velocities that don't put them very far away from us. If they're only detected in atomic hydrogen, because they're so close to us and could be in the galaxy or could be close to the Milky Way galaxy, we can't use their redshift as a distance indicator, and there is no other way to measure the distance. And so there's been a lot of controversy over time as to where those clouds come from. I think our understanding is that there's a lot of stuff going on in the region around the Milky Way, and there's material being still accreted by the Milky Way. The Milky Way isn't a group. The Milky Way has been beating up on some nearby galaxies. The poor Magellanic Clouds were kind of mean to it. But there are some other clouds like Leo P. When we discovered it, was classified as a high velocity cloud. And it was only when we were able to measure the distance from the HST image, and there was actually an earlier ground-based image that gave us a good handle on the distance, that we were absolutely sure that it was a galaxy, not a cloud in the Milky Way. It's complicated. As complicated as I like to tell my students, all the easy stuff has already been done. It was done by us when we were students, and it wasn't easy then.
Yeah. Martha, thank you again very much for sharing your Friday evening with us. Everyone, I'd like to bring this to a close. Likewise, I would like to thank everyone for your interest and participation in the Jansky lecture this evening. As I was counting participants, we had over 200 people in attendance. I think that attests to Martha's wonderful abilities as a speaker, is an inspiration to all of us. Everyone, thank you again for attending. I will make a couple of advertisements. Martha will be giving this lecture again for our counterparts in Charlottesville next Tuesday evening, November 17th. And another plug for everyone, we will be having a VLA virtual tour on December 5th at 1 p.m. Again, thank you everyone for your participation. Have a wonderful and safe weekend.